All right, let's go ahead and get started. Here. All right. Here's your Halloween joke. You can can see that? All right. Yeah. And now that you've taken this class, you understand this. So all right, so let's go ahead and do some announcements. Yeah, as always, try to keep the talking down to minimum when we're doing the lecture stuff, just for everybody's sake. No new assignments, so no hand-in this week. There's the recommended problems is just like the first 3 in chapter 13. And then if you're looking for more problems, you could start on the chapter 13 online homework. Do the ones that aren't about confidence intervals on there. So I went ahead and made the whole assignment due next Friday, because some of them are about confidence intervals, and I didn't want you to have to cram that right before the test. Exam number 2 is this Thursday from 6 to 7:30. So preparation. All ordinary office hours will be held, and then you can go to those, bring questions, ask questions in those. There's a study jam tonight, 6:30 to 9. And then I will do a review session on Tuesday night at 6 to 7:30 here, like we did last time. And you can bring questions to that as well. I'll bring some questions to do through all the chapters. And then Thursday, there's a study jam on Wednesday night. Go to that, 6:30 to 9 p.m. And then the Thursday lab is for review purposes like last time. All right, any questions on the exam or anything like that? Yeah. Oh, okay, yeah, it's chapters 8 through chapters 13, and that's through page 191 in the course pack. So it's the part about the central limit theorem, but not the confidence intervals. Any other questions? Yeah. Tonight's Monday. No, there isn't. Because yeah, we've already done chapter 12. That was last week. Yeah, so no online homework tonight, but it'll be due, yeah, to next Friday. Question? Oh, it was due tonight. All right, it must be due tonight. I thought it was due last Friday. I guess get the days mixed up. My bad. It says it's due tonight. It must be due tonight. All right, any other questions? Yeah, thanks. Yeah. All right, so let's get into confidence intervals. So today will be all about capturing the parameter P. And what I mean by that is that we would like to try to find what the parameter P is. And we can use a sample statistic for that, P hat. So that's what a confidence interval is. It's a interval where P is likely to lie. All right, so we don't actually know P because we're taking the sample and we don't do a census of everything. But we don't want to just have some kind of subjective, like, oh, we think it's close to here. We can use a mathematical formula to find this interval. So let's go over that. It uses the central limit theorem. But before we get into all of that, let's think about this using the 68, 95, 99.7 rule. All right, so we've got a p hat that arises from a SRS. So from a simple random sample, we get the p hat, and then this is what we know about p hat from the central limit theorem. Just a little bit of a review here. That it's approximately normal, centered upon p, and standard deviation is square root of pq over n. All right, so if we use this 68, 95, 99.7 rule, we can say that if we keep taking samples, that we'll get samples, 68% of the samples will have a p hat that's within square root of pq over n. So this is one standard deviation right there. And then 95% of the samples will have a p hat that's within 2 standard deviations, and so on here. So that's just summarized in this picture here. That says that the p hat is likely to fall around where p is. And within 3 standard deviations there, we for sure, we most likely have p hat. 99.7% of the time, p hat will be within this interval right there. All right, so we have an interval here. So try to make a little bit of a connection where we might find our interval. So looking at this picture. So it's a little bit different than just looking at this, because we start with the p hat and then we're trying to find p. But if you look at this picture here, we've got p is labeled here, but we don't know where p hat is. All right? Just want to point that out. All right. So there's one issue with these numbers right down here. And what that is that we're using P and Q to find the standard deviation here, but we don't know P, so that is a big issue. All right, so the problem is we need to know P there. And so what you want to do is we want to use p hat to estimate p. All right. All right, so now instead of calling this a standard deviation, we call this a standard error. It's really close to the formula that you learned for the standard deviation. The only difference is that instead of P and Q, we have P and Q hat. All right. You see the difference there? So it's an important difference because you use different numbers for these. So if you knew P, that could be something like 0.4. So say P equals 0.4, but you could get a P hat of 0.3, something like that, something different. So here you you'd say the standard error of p hat. And notice I'm not writing a number in here. That's because this is the distribution of p hats. That's what this symbol means right there. It's 0.3 times 0.7 all over. For example, we could have a sample size of 100. Right there. And that's how you'd find the standard error. The standard deviation of p hat would be 0.4 times 0.6 over 100. All right, so the standard error it's estimating the standard deviation of the sampling distribution. So it'll be close, but it may not be perfect. All right. Any questions with this? Any of the symbols or anything? All right, so let's do an example here. So we've got a Gallup Healthways well-being poll. Asks 1,000 Americans whether or not they had a cold yesterday. So there's a general pattern. Usually in December and January, there's the highest number of colds, and then lowest in July and August. All right, so here we've got a sample statistic right here. Sample statistic p hat equals 7.1%. And then we've got the p, the proportion of all US adults who had a cold on January 14th. Yeah, make sure you know how to define what the parameter is and what the statistic is. All right, so let's say that we had the 1,000 respondents are in SRS, and then the standard error of p hat is right here. So we take p hat was 0.071, so we took that from up there, times 1 minus 0.071, all over 1,000, and the square root of all of that. And you get 0.0081. All right, so this is a standard error. And now we use that empirical rule to say something about where all the samples are. So we're trying to capture that P, remember. So right now we know that we've got samples, 68% of the samples of size 1,000 are within 0.0081 of P. So we're pretty close to P, but we don't know plus or minus. It could be either one. So this within, that's where you get a plus or minus from, because you don't know if you go to the right or to the left. All right. And then all this number is 2 times 0.0081. And then we've got 3 times 0.0081. All right. So with a wider interval here, so plus or minus 0.0162, that's bigger. We have a higher percentage of samples within that range. All right, so try to link that, make a connection there. So a wider range gives you a higher percentage of those samples. All right, so interpretation of this. So we don't know whether the p-hat of 0.071 is within 0.0162 of the true p or not. But we do know that 95% of p-hats from SRSs of size 1,000 are. So this is where you get the confidence interval from. So we have p-hat, and then we could go plus or minus this number 0.0162, and that tells you the interval, and then we got that number from the 95% line here. So this would be the 95% confidence interval. All right, when you write this interval, use interval notation, which is you've got a parentheses, lower bound, comma, upper bound, end parenthesis. So what this is saying is that we've got an interval from 0.055 to 0.087, right there, and that we're 95% confident that we've captured P within this interval. P, parameter. That one, it's about how many people had a cold yesterday, or said that they had a cold yesterday. So it's not of the 1,000 respondents, it's of everybody. I suppose this is in the US. Gallup polls are usually just US, I think. All right. So here's a new word for you. So we learned what a confidence interval is. And we'll do some examples with that, because it's kind of a little bit of a complex idea, I guess. But part of this confidence interval, we've got a margin of error. So that's how much you go plus or minus. So margins are on the sides. So we've got a plus or minus a certain amount. And then, yeah, that's what I said. So in polling, they just always use the 95% confidence interval, but you can, but we can use different confidence intervals. All right, so here's a question: why did we use 2 times the standard error as the margin of error for a 95% confidence interval? All right, and that has to do with the 68, 95, 99.7 rule. So that's why we know that we use twice the standard error of 0.0081. All right. So this is based on the 68, 95, 99.7 rule. Okay. go. All right, I think I want to draw a picture for you now. So let's say we had a p hat right here. And then let's say we wanted to be 95% confident that our interval would capture p. So a way to look at this is you could have normal distribution right here. This one is centered on p. But then we don't know that p is greater than p hat. P could be less than p hat. So we could also get something like that. And then p would be right there. All right. So we've got an interval from one possible place the p could be to another possible place that p could be. And the way I drew this was so that we would have two standard errors right there, and then two standard errors this way, right there. All right. So at least I kind of like thinking about it like this. If this really confuses you, you can throw it out. But I like thinking about how p could possibly be lower than or greater than p, or p hat. So you could go to the left or go to the right. And that this interval right here is capturing that p right there. So if you look at the purple or the red just by itself, that'd be less confusing. And you could see that, so like for the red normal distribution here, p hat is within 95% within two standard errors of p. So 1, 2, it's right on the edge there. And then if you look at the purple one, the p hat is right on the edge of two standard errors away, but on the less than p instead of greater than p. And then of course, p could be somewhere in here as well, but then p hat would be really close to p. And it would be within two standard errors from p. All right. Does that kind of make sense? Let me kind of go over that question. Oh, they're right on top of it. It's because we have that's the furthest away. We want to these are the furthest away that we could capture p. So they're right on top of p hat right here. Question? Oh, yeah. Mm-hmm. Okay. Yeah. So I could draw another picture here. Yeah. I think this will make sense. So you start with the p hat, and then you have a margin of error right there. So this is a little more like a stripped down version of the picture I drew on the left. So here we've got the confidence interval is this line. So P, we're 95% confident that this interval captured P. So it may not have captured P, but we're pretty sure it did. Right? So this one is probably easier just for your to try to figure out, oh, what's the margin of error? It's half of this width. Or if you knew the interval and you wanted to find p hat, you'd know that it was exactly in the middle of the confidence interval. You could work backwards from that, from this little picture right here. All right.
Yeah, there's like two SPP hats and SP.
So the margin of error is with us SE. Yeah, and that's the margin of error for 95% confidence interval. All right, so we need to find a critical value, Z star, such that 95% of the area beneath the standard normal curve is between minus Z star and Z star. So what this is saying is that instead of 2, we may be able to find a number that's a little more precise instead of using the 68, 95, 99.7 rule. But we could do like 1.5 times the standard error or 1.8. And we actually have a table on the next page. We call them critical values, Z star, where the Z star for 95% level is 1.96. So that's really close to 2, what we used on the previous page. So you can make a link there, make a connection there, that this 1.96 is kind of like using that 68, 95, 99.7 rule. All right. Oh, no, I'll give them to you. Yeah. So on the, this will be on the final exam, but I'll actually give you a page of notes to use. So you'll get a little more to work off of. So you don't have to memorize like the conditions for using a central limit theorem for proportions and for means, and then I'll give you these. It's pretty much just this as well. Critical values here, but we can actually find these. We can find these using inverse norm. So here, let's work off of this. So we want to find Z star such that negative Z star to Z star are the boundaries for 95% of the area under this normal curve. So what that means is that we've got 0.025 right there. And then we've got 0.025 there, the area and the two tails. One note here is in this class, we'll always have confidence intervals that are centered on 0. But there are cases where maybe you would like to have a little more margin of error on one side than the other. If that makes sense. So if you're more concerned about like a bridge collapsing as opposed to a bridge being too strong, then you'd probably want a little more margin of error on the safe side than on the other side. All right, so to find what Z star is, we'd use inverse norm. And the percentile here is 0.975 is where Z star is. And then your calculator automatically assumes that the mean is 0 and the standard deviation is 1. So we go to second distribution, inverse norm, 0.975. And we get 1.96, and that's our Z star. And then negative Z star is just negative 1.96. All right, so we could find for 0.99. Okay, move that. So let's say we wanted 0.99. And we wanted to find our critical value. Right there. So now we would have 0.005 on this side and 0.005 over there. And we would take inverse norm. And we want to find Z star for starters. So it would be 0.995 because we had to add this amount. So 0.99 plus 0.005 would give this inverse norm here. And we have 2.576 right there. So it's nothing new here. We're just, you'll see that that's in our, it's in our table here. Right, right there. 2.576. And let's find, no one ever would use a confidence level of 90. Well, how about we find 99.9%? Maybe we need a lot of confidence that we've captured P. So for that one, we'd have 0.999 within. We're looking for Z star. And we would use, well, we'd have 0.0005 right there. And here we'd use inverse norm 0.9995. Right there. And that would give us a 3.291 for our Z star. All right. So that would be like if we wanted to get more of these numbers right there, 3.291 right there. All right, any questions with that? So this is what you'll want to remember down in the box, lower, a little lower down the page. So you want to remember that. Yeah, let's just go up there. So to find a one proportion Z interval, we would take p hat plus or minus Z star times the standard error of p hat. So this is just putting it all together here. So instead of using 2 or 1 or 3 like we were doing with the 68, 95, 99.7 rule, it would depend on your value in the table here. You could use like 1.96 for Z star. And then with this formula, you can do a lot of like, let's say you know Z star and the standard error, you could find what p hat would be because you know p hat is precisely in the middle there. So if you knew the confidence interval, like down here, you could work backwards, so to speak. All right, so we've got the standard error is right here. And then we've got the margin of error is right here. Margin of error. All right. So margin of error is just some multiple of the standard error. All right, so let's just let's look at this example here. So 95% confidence interval, we would take the p hat plus or minus Z star times the standard error. So it'd be 0.071 plus or minus 0.059. And then what you do, well, maybe I'll zoom out a little bit here. All right, so you take 0.071 plus 0.0159, and that gives you the right, the upper bound here on your interval. And then second enter, and you could just switch this to a minus sign, and that would give you the lower bound right there. So that's where you get those two numbers from, the 0.055 and the 0.087. All right. So let's do some problems. Let's say we had 90% confidence interval of 3.25 to we're still in proportion land. So let's use a number that you will actually see. 0.36 to 0.45. All right, so we have a confidence interval here. What is p? What is margin of error? What is p hat? All right. So with this, it's helpful to draw a picture. So we've got our confidence interval, and then we know the lower bound and the upper bound. So you just write what you know about this confidence interval. And then we've got some blanks here. We don't know what the margin of error is just yet, and we don't know what the p hat is. It'll be easiest to find the margin of error first and then find the p hat, because once we find the margin of error, we could just subtract that off from 0.45, and then we know where p hat is. Right. So the margin of error is half of this distance. So 0.45 minus 0.36 divided by 2. Can you see that? Oh, like we don't need to know that it's a 90%. Yeah. So you would need to know the 90% if you want to find the standard error for in this problem. So maybe that'd be a third question. What is standard error? P hat. Yeah, because no matter what confidence level you are, the confidence interval looks like this. So you work that out. It should be 0.045. And then you would subtract that off from 0.45 to find p hat. And that would give you 0.405. Right there. And then for the standard error, so let's use what we know here. So we know that margin of error equals z star times standard of error. No. Margin of error equals z star times standard error of p hat. And we now know margin of error. And we know z star from our table. So z star is 1.645. And now you could just solve for the unknown. All right. Any questions so far? Kind of with me? So this is just like some kind of problem you may see, like you should know how to work with the confidence interval, how to work with this formula up here. It's not as bad as it seems. Don't get bogged down with the whole plus minus thing. A lot of times if you're solving, you can just use the plus side of things. You don't have to think about the minus side of things. So here, let's just finish this out. Standard error of this is equal to 0.045 divided by 1.645. 645. and that is 0.0274 right there. All right, so I want to just say some general things that are happening with this formula. So as n increases, the margin of error, the standard error is getting smaller. So that means the margin of error is getting smaller. So that means that your confidence interval is getting more narrow. So, and then with p hat and q hat, if the largest that can be p hat times q hat is 0.5 times 0.5. It's the largest value you'll get there. And then you can get really, really, really small values by taking like 0.0001 times 0.9999. That'd be a pretty small number right there. And then with Z star, the higher your confidence level, the wider your confidence interval. And then all p hat does is place your confidence interval in a different location. It moves it around. All right, and then let's go ahead and end here, and we'll pick up on Wednesday. And I'll try to do some review problems in class as well, just like a 1 or 2. So.